Okay, so this is really just a lead up to momentum. We're not actually starting momentum yet, so this is kind of your introduction to Physics 30. Some of it is just review, some of it is a little bit new to you, but let's get started on proportionality, which we did go over in Physics 20, but we're going to go over again in Physics 30 because it's going to show up again, and I might say even more than in Physics 20. And of course, what is proportionality? It's just knowing what happens to one variable if one other variable changes, right? So for example, one that we looked over a lot in Physics 20 was if I change the force that something experiences, what happens to its acceleration if their mass stays the same? And so those two variables that you're comparing have to be on opposite sides of the equation. So with force equals mass times acceleration, force is on one side, acceleration's on the other side, so that's good. And then of course, we're going to keep whatever other variable constant. So for example, in force equals mass times acceleration, mass would then stay constant because I just want to know the relationship between force and acceleration. And so of course, in that case, we would need our controlled variable, which would of course be mass. Okay? And then if you remember, if we actually want to write a proportionality statement, we use this symbol, to represent proportionality, and it's that fishy symbol. It looks like this, and that means is proportional to. Okay, so let's do an example of this, but with a slightly more complicated equation than F equals ma. So I have this equation here, which you guys don't know about yet, but you will when we get to electric forces and fields. This is Coulomb's law. And so I want to know the proportionality between F and each variable given in the equation. Okay. So for example, what's the relationship between F and Q1, F and Q2, F and R? I'm not going to look for the equation between F and K because K is a constant, okay? So that's not really a variable, okay? So this is electrostatic force. Q1, Q2 are the charges, and R is the distance between the charges. So again, I'm looking what happens to the force between the two charges if I change the charge of one of them or charge to the other one, or the distance between them. And so what do? Well, I ignore everything else. So for example, if I'm looking for the proportionality between F and Q1, I basically ignore everything else. I just ignore it fully. And then the only thing we wouldn't ignore is exponents. So things like to the power of 2, or technically a square root is an exponent. So we wouldn't ignore that either. But I'm going to ignore any other variables. And then what I see here is that force is just directly proportional to Q1, right? Because there's nothing being squared there. It's not, when we look at the fraction, it's really on the top of the fraction. So now it's as good as being over 1, okay? And so then if we do the same thing with Q2, we'll notice the exact same thing where Q2 is still on the top of the fraction, and then I got rid of the R squared. So it really doesn't change. Force is also proportional to Q2. So what does that mean? It means if I change the charge of one of the charged objects, then the force will change by the same factor, right? And that's what that means. But of course we have one more, and that is R, because K is a constant, so we don't care about that. So when I'm looking at R, again, I do ignore everything else. I just say, okay, well, now this whole numerator is ignored. Only thing is, R is in the denominator, and it can't change that, right? We can't just say force is proportional to R squared, because it's not. It's proportional to something over R squared. But again, since we're ignoring all that, we're just going to put a constant in there. And what better number to be a constant than 1? Because 1 doesn't really change anything. And so that's how we would write that proportionality statement, is that force is proportional to 1 divided by the distance between the two charges squared. So that is not just an inverse relationship, that's an inverse squared. So basically, whatever I do to the distance between them, square that, and then do 1 divided by that, and then that's what's happening to the force, okay? So they're the opposite, and then plus it's being squared. So if I triple the distance, well, and I take the distance, square that, so triple 3 squared is 9, and then instead of being 9 times as much force, I'm doing the opposite, so I'm dividing by 9, so that's 9th as much force. Okay, so those guys are an inverse squared relationship. And there is all the relationships between all the variables in that equation, which of course k is a constant, so we don't care about the relationship there. Okay, we got a few more questions here. So if each charge doubles and the distance triples, what happens to F? Okay, well, this one's different where instead of just one of the variables changing, all 3 of them are. So the only thing that's not changing is k. So if I know that's going to happen, but each charge doubles and the distance triples, if I want to know what happens to that, well, I just assume that everything was 1 before, and now I'm going to double both Q1, Q2, so that's going to be 2, and I'm going to triple R, so that's going to be 3. So just assume everything was 1, right? Q1 was 1, Q2 was 1, R was 1, and then do whatever the thing is trying to tell you to do. So F is equal to, and then the K remains constant, so that's just going to be there. That's not going to change. So what we actually do is, again, if something's not changing, we kind of ignore it. Q1 is going to double, Q2 is going to double, and the distance between them is going to triple, but remember we have to square the distance, okay? And so what does that end up being? That's 4/9, so that means the force is 4/9 as much as the previous force. So it doesn't matter that we doubled both the charges, of course that distance makes a much bigger difference. So the new force is 4/9 as much of the previous F. Okay, and then what if the force is 250 newtons and one charge is reduced to 1/3 of its original value and the distance is reduced by 1/2 of its original value? Now calculate the new force. So we're going to do kind of the same thing that we did before. So now the new force, I'm going to figure out, well, we know it's k q1 q2 over r squared. Just assume everything was 1 before and change kind of what's going on. So of course the k didn't change. We'll say q1 was changed to what it's reduced to 1/3 of its original value. And then the other charge didn't change, so I'm going to ignore that as well. So k and q2 are ignored. And then I'm changing the distance, so I should probably divide that by 1/2. But then I got to square that because we always square the distance. Okay, so what does that equal? Well, that's 1/3 over 1/4, which who would ever write a fraction with 2 fractions in it? That's insane. So that actually ends up being 4/3. So all that's telling us is that the new force is 4/3 as much as the previous one. Okay, so what do I need to do? I need to take the original 250 newtons and I need to multiply that by 4/3 because that's how much the new force will be. It's 4/3 as much. Okay, and then if we do that, we calculate that, we should get 333 newtons. And there we go. So that's how we also use proportionality to solve something like that. Okay, and that is definitely something you will see in Physics 30. Okay, now let's talk about graphing a little bit. Hopefully you're all fantastic at graphing. There's going to be a lot more graphing in Physics 30 than there was in Physics 20, and there was already some in Physics 20. So these are the rules you always have to come back to. I say do not copy just because, well, you should have heard them a bunch of times by now, so this is really just review. But oh my goodness, please come back to this video anytime you have to graph anything, or at least these notes. Because please, 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 you need to follow these rules for graphing to get full marks on graphing. Okay, so first, please use more than half the graph paper. So for example, if you have something where like you're not going up enough and then you still use most of this part, but it's still not half, well, you could have just doubled that and gone all the way up there, right? So it makes no sense to use less than half the graph paper, because if you're using less than half, you could have doubled one of your axes. Okay, sometimes, however, you don't have to use the full graph, because I've seen it where people, they're like, I can use more of the y-axis if I go up by thirds. The thirds are like the bane of your existence, because then trying to interpolate between like 3 and 6, if you have like, I don't know, 3.7, trying to interpolate where 3.7 is, it's just not fun. So in that case, I would say go up by 2s and use a bit less of the graph paper, but then you're still using like 2/3 of the graph paper. So if by thirds you're using like this much, but using 2/3 you're using maybe that much, that's okay. That's fine. So use at least half the graph paper, but sometimes if you're not using all the graph paper, but it's at the expense of having nice axes, then absolutely make that the expense of it. But if you're using less than half, you can double one of your axes. It makes no sense. Oh my goodness, please, please, please have a title on your graph. That's the most annoying when I have to take off a mark because somebody didn't put a title on their graph, because the easiest thing to do just needs to be the responding variable versus the manipulated variable, which of course changes depending on what relationship we're looking at, okay? The responding variable should always be on the right column of your data, and the manipulated variable should be on the left, okay? So really here it should be manipulated, and responding should always look like that, okay? Because guess what? Manipulated is your X and responding is your Y. And that brings us on to axes. So label your axes with variables and units. So remember, your x-axis is your manipulated variable, which again comes back to this. Where in a table, we usually have x first and then y. So x on the left, y on the right. And then, of course, on our graph, that goes to the manipulated here because that's on the x, and the responding on the y, okay? So please, please, please follow those rules. Very, very important. Because scale your axes appropriately. This is what I was just talking about. Sometimes going up by thirds is okay. Most of the time, going up by thirds is the bane of your existence. So make sure you have nice intervals. Also, make sure that each division is equivalent. I know it sounds obvious, but I've seen this. I've literally seen this, where somebody is like 1, 7, 8, 12, like what? No, that you're going up by 6 and then by 1 and then by 4 and like, no. So you're going up by 2s or 4s or 6 or 0.5s or 0.25s or 0.1s, I don't know, but you're going up by the same number every single time, okay? And then, of course, the divisions might not necessarily match the numbers in your manipulated column, so you just choose divisions that make the graph construction easier, because sometimes the ones in your manipulated column are crazy decimals, and you might just need to go up by 0.5s or 0.25s or something like that, okay? Obviously, plotting the points, that's pretty straightforward, but then the line of best fit isn't always as straightforward. You do not just connect dots. Again, it seems like I shouldn't have to say that, but I do. Do not connect the dots. We're not playing a game of connect the dots here. It won't make a pretty picture. So either you figure out what is this going to be a line of best fit? Is this going to be a curve of best fit? A lot of the time we have an accompanying equation for the graph, and that equation helps tell us what kind of graph it should be. So in physics 30, a lot more you'll be expected to notice curves of best fit more so than in physics 20. Okay, so it can be straight or curved, but it should represent the trend of the graphical information. If it's straight, please use a ruler, okay? Don't just try to go for it, no. Just please use a ruler. Something straight to draw that straight line of best fit. If it's curve of best fit, again, it's gonna have a clear like inverse relationship or quadratic or square root relationship, and we will go over what all those different graphs look like. So for example, you guys have probably seen this before, probably in Physics 20 with me, which is the best line of best fit in this diagram, A, B, C, D? Of course it's D, because A is just connecting the dots. B is too high, C is too low. D, oh, well that looks like it's basically going through the middle of all the data. It's not just connecting dot 1 with the last dot, right? Which is what we do. We try to make it go through the middle of all the data and accurately represent the trend as much as possible. Okay, but again, like I said, in Physics 30, we might see more curves of best fit. So this is what a lot of your graphs can look like. Obviously, you should hopefully know what a linear relationship looks like. Okay, so that would be, for example, F equals MA, right? Mass being our constant, and then A being on the x-axis, F being on the y-axis. And so if you're changing the acceleration of something, you must be changing the force of it, and then that's a linear relationship. We have a quadratic relationship, which hopefully you know what that looks like. So that could be a quadratic like that, or even like this, right? Those are both quadratic relationships, but that's when you're squaring something. Okay. The ones, if you haven't yet taken Math 30, here's a few others that you do need to know the shape of. So an inverse graph. So this is just, for example, the equation we just went over, F equals Q1, Q2 over R squared. Well, if Q1 and Q2 and K are all constants, then what's on our y-axis would be force, what's on our x-axis would be distance, and this would be, actually, oopsie, this would be an inverse squared relationship. I should have written it down there. Because R, the distance, is in the bottom of the fraction. Okay, so this is a type, but this is actually inverse squared. So inverse is inverse squared. They have very similar shapes. Inverse squared is just like if this is your x and y axis, it just hugs it even more. Okay, so that's what inverse graphs look like. And then a square root graph is at the bottom here. So you notice they're all kind of nice, smooth curves. Okay, so if you've taken Math 20 and you know what a quadratic looks like, basically just change the orientation of a parabola, and that's basically what everything looks like. And this is, of course, all of these are thinking, okay, if that's your x and y axis, because usually in physics we only look at the positive x and y axis. We rarely go into the negatives. Okay, and that's what that looks like. So make sure you know those graph shapes in general and what they look like. Because that takes us on to linearization. So the thing is, at this point, even at a Math 30 level, you can kind of deal with these graphs, but linear graphs are always the best. They're always the ones that help us analyze data the most. So if I have something like an inverse or an inverse squared or a square root graph, I want to turn it into a linear graph, because we know this from Math 10, y equals mx plus b. The slope in physics always tells us something really important, right? So for example, in Hooke's law, it told you the spring constant. And then b, if it's not zero, if the y-intercept's not zero, that also usually tells you something really important. So linear graphs just help us a lot. So we need a process of then being able to take any of these other graphs with curves and linearize them, make them align on a graph, okay? This is a brand new process to you, so pay attention, because it's not exactly simple. Well, I think it's simple, but I've been doing it a lot longer than you, which is no time whatsoever. Okay, so your first thing to do when you're trying to linearize a graph is, well, you just graph the data and determine the relationship. You're like, oh, that's a inverse relationship or a squared relationship or something like that. And then what you're going to do is you're going to take what's on your x-axis, your manipulated variable, and you're going to calculate new values based on the relationship. So if it's a square relationship, you're going to, guess what? Square all the things on your x-axis. If it's a square root relationship, you're going to square root everything on your horizontal axis, on your manipulated axis, and then you're going to regraph based on the new values, and you will have a nice straight line. vertical axis is always going to stay constant, okay? So always just remember you're always calculating new values for the horizontal axis, but your vertical axis is always going to be constant. So please remember that. And then you can determine the equation of the line and what the slope represents and so on and so forth. So let's do an example of this because it will be much more obvious when I do an example. So for example, say this is a distance time graph I have, which is clearly a quadratic relationship. And since it's quadratic, not linear, I can't analyze it exactly the way I want to, okay? But I can see here that distance is proportional to time squared, okay? So this is something that's speeding up. It's not covering the same distance over time, but I want a linear graph. So how do I linearize this? How do I make it linear? Well, again, so what was our step? So we graphed the data. There we go. We determined the relationship, a squared relationship. So it's a quadratic where displacement is proportional to time squared. Again, how do I know this? Well, again, a quadratic is y equals x squared. What's on the y-axis? Displacement. Oh, what's on the x-axis? Time. Oh, so I just replace y with d and x with t because that's what's on each axis. Okay? So there's my new, there's the relationship between those two. So what does that mean? That means then my horizontal values, time, I need to square them all. Okay, so right now I have 0, 1, 2, 3, 4, 5 for my times. So I'm going to square all of those, make a new table of values. Okay, so now in my new table of values, we're keeping the distance the same. This is still saying that staying the exact same it was before. So if you look 0, 1.2, 4.8, 10.8, 19.2, 30, and they're exactly the same as these guys right here. Okay, so that didn't change, but what did I do? I squared all these. So I'm going to square 0 and 1 and 2 and 3 and 4 and 5. And hopefully we all know what those answers would be. This would be 0, 1, 4, 6. Oh, no, apparently we don't. 4, 9, 16, and 25. And look at that. That is what we have. And then when you graph it, look what happens. You get this beautiful straight line. Okay, so and if you notice, this is now not distance versus time, this is distance versus time squared. So also when you're linearizing, please change your axis. It will only be your horizontal axis, of course, because that's the one that is changing. So whatever you did, that's just, you can just put it like, you can do time squared, and then your units are now seconds squared, right? If we square rooted, we'd just write the square root symbol with time underneath, and then your units would be square root of time, okay? So that's all you have to do for your axis. And now, of course, you also see that the title has changed, distance versus time squared, okay? So you do need to change that in your title and the title of your axes as well. But there we go. We have linearized this graph because, again, we saw, oh, it's a quadratic. What does that mean? That means that I need to square the horizontal axis because I only ever do things to the horizontal axis, okay? So say I want to determine the equation of the line then. Well, hopefully you remember how to do that from Math 10. First, we're going to calculate the slope, which again is change in y over change in x. So I'm going to choose 2 points. Now, usually if it didn't line up this nicely, I would absolutely make you find 2 different points on the line. But because they all line up so perfectly, I'm just going to choose 2 points that were actually given to me in the table. But usually you're not allowed to do this. Okay, usually you have to find 2 brand new points on this line. Okay, but let's do this. So what is this? This is 25 seconds squared and 30 meters. And then this guy is 4 seconds squared. Oops, I didn't mean to do the end of the thing there. Okay, so 4 seconds squared and what is that? 5 meters. Okay, so those are 2 points, change in y over change in x. So 30 minus 5 is the change in our y-axis, and change in the x-axis is 25 minus 4. And what do we get for a slope when we do that? We get 1.2. And our units are really, really important because they either tell you something or tell you what something's going to do with. And what do we have here? We have meters per second squared. Seems really important. I feel like we've seen those units, meters per second squared, before. So that might be telling us something really, really important. Okay, let's keep going. We got to calculate the y-intercept. Okay, we all know the y-intercept is 0, 0. Okay, like we all know it's going through the origin. Just in case you forget how to do this. So by the way, y equals mx plus b, but I replace y with the variable that's on the y-axis, which is d. M, which is our slope. X is now times squared. You do need to put the squared in there. Plus b. Okay, well, what do we do here? Well, when you want to calculate b, you need to substitute in a point for d and t squared. Okay, so I'm going to use this guy up here, which was 25 seconds squared and 30 meters. And so I'm going to substitute in 25 for t squared and 30 in for d, and then of course my slope in, and then I should be able to get b, the y-intercept, which of course would just be d times the slope times t squared. Okay, so that's what I'm going to do, which is going to be, again, 30 meters minus, my slope was 1.2 meters per second squared, times, now remember, this is already squared. So you don't need to square it again. We're using t squared, but remember that time has already been squared, so don't need to square it again. And what do you get for b? Surprise, surprise, you get 0. So that was just an example of how you find the y-intercept. Just as a refresher, we knew it was 0, 0. Okay, or that at least it went through the origin. But that's how you do it. You substitute in your slope, and then you substitute in any point on the line. Okay, for your x and y. So there we go, and we can now finally write our new equation. Remember, again, you do need to include the new symbols, and your slope should also have its units. Okay, and that is my new equation. Of course, I'm not writing the plus 0. So anyways, there we go. That's it. That's going to help us figure out what's going on here. Okay, and now I can use that equation to find anything else. So for example, now we're going to use the equation to determine the distance a car travels in 15 seconds. Oh, well then I just need to plug in 15 for time here. Now, keep in mind, when I was plugging in from my graph, my x-axis had already been squared. So wasn't worried with squaring that 25 because it already had been. This 15 has not been squared, so I should probably square it, okay? And when I do that, I get 270 meters. So that's nice. That's a whole equation that we came up with just on our own. So if this thing keeps accelerating the way it is, then there we go. And then also we're going to use the formula on the formula sheet, hint a kinematics formula, and your slope to determine the acceleration of the car starting from rest. So our slope wasn't exactly our acceleration. I know it has the same units, it's meters per second squared, but we can't just automatically assume that that's our slope. It definitely has to do with it. Okay, so remember, our slope is d over t squared. Okay, that's what we really have to keep in mind with our slope, because again, this was your displacement, this was your time squared. So it's always good to recognize, oh, that's my slope. Because then this is something that you didn't do at all in Physics 20 that you're going to be doing more often here. Okay, so please pay attention. You're going to be taking an already existing equation and you're going to be looking for this in the equation, d over t squared, okay? So the equation I'm going to use is a kinematics equation because I know my initial velocity is 0 and I know that I don't know my final velocity at all because I don't even know when this is ending. So I'm going to use this one because, again, it either deals with dt squared, what I know, it deals with acceleration, what I'm trying to find out, and initial velocity, which I also know, and I know that one's 0. So I can get rid of that whole thing right there, which means displacement is equal to 1/2 at squared. What were we trying to find again? The acceleration. How do we rearrange this for acceleration? Well, that would be 2 times displacement over t squared. And here is where we're going to use the knowledge of our slope. Because what did we know about slope? Slope was d over t squared. Oh my goodness, look at that. Okay, so that's why our slope wasn't exactly the acceleration, but it's definitely going to help us find the acceleration. So what is this really? It's telling us that our acceleration is really just 2 times our slope, okay? Which is, of course, 1.2 meters per second squared, which is then equal to 2.4 meters per second squared. Okay, so that's a brand new skill for you guys where you're like, okay, well, I think slope is telling me this. I think slope is telling me acceleration. And then you find out, okay, it's not telling you the exact acceleration, but it definitely is going to help us find that because we still need to be able to go back to our formulas that deal with acceleration and find the pattern, find the slope in them. And again, here I solved for acceleration and I found, oh, look at that. My slope is technically right there. Okay? Something we'll do more of as we move on, but there it is introduced to you. And there's just the first few parts of Physics 30, or the things that you need to know going forward. In Physics 30, we're going to do one more kind of review thing here with some systems and energy, and then we'll really get onto Physics 30 with momentum.